everybody. Remember I said that I need you to memorize the strong acids and the strong bases, and that there would be a quiz. We decided on Tuesday of next week, I think. So kind of bear that in mind. Hope you're starting to study that stuff. Let's review super fast real quick. Look, the janitor didn't make it in here yesterday. We have a dirty board. That's okay, we'll survive. Let's say that I have this chemical here, and I react it with water. Well, I end up with this as one of my products, okay? If I form this as one of my products, is this chemical acting like an acid or a base? Acid. How do we know that? What's that? It loses the H, right? So the H had to come off of that thing and go onto the water in order to form this product, right? So it had to be acting as an acid. Now, technically, it was capable of also acting like a base. Anything that contains an H can give it away and act like an acid. But anything that's negative can accept an H and act like a base. So actually, this thing could have acted like a base, but in this case, it's acting like an acid. What do you call a chemical that could act like both? Uh-oh. Amphiprotic. Amphiprotic. Amphibian, right? Land and water, right? Amphiprotic, acid or base. How can you tell it's going to be amphiprotic? It's got the H, it's got the negative. Those are the two keys that we're looking for. Okay, so now tell me, what's the other product going to be? If I take the H off of that chemical, what am I left with? SO4, and there's a major detail we still have to put on here. Not positive. Remember, we're taking off an H, but it's not just an H that we're pulling off. We're pulling off an H positive. Well, this thing was negative. If I pull off a positive, it's going to make it more negative, isn't it? If you remove another positive, it's going to make it more negative. So it should end up being -2. Does that make sense? Okay. Guys, if you have a positive and a negative, it's neutral. This is negative. What it means is it had an extra negative on here. So if I take off that positive, what am I going to be left with? 2 negatives, right? So whenever you have a chemical and it's got a negative charge on it, if it's going to lose an H, it's going to become more negative every time. Just one more negative. Okay, so we have a tiny bit more that I need to give you from the notes. If we call this an acid, then we're going to call this a base. We went over that part yesterday, but here's the new part. We're going to call these two chemicals conjugates. So this is a conjugate, and this one's also a conjugate. One's going to be a conjugate acid, and the other is going to be a conjugate base. So how do we determine if this is a conjugate acid or a conjugate base? Well, just look at it. Look at its charge. Can this thing act like a base? No, it's not negative, is it? But can it act like an acid? Yes, it has an H it can lose. This can act like an acid, so it would make sense to call it a conjugate acid. How about this guy? Well, it's negative, isn't it? It can act like a base. Can it act like an acid? No, it doesn't have an H to give away. So it only makes sense to call this one a base. We're going to call it a conjugate base. So on this side, you have your acid and your base. On the product side, that's where your conjugates will be. Now, I want you to notice something. If water is a base, the chemical that it turns into is a conjugate acid. And that's always a fact. That's always the way it's going to be. This chemical was an acid, right? So the chemical that it converts into is a conjugate base. So if you can identify the acid, just find what it becomes on this side, and that will be the conjugate base. If you can identify the base, then what it becomes will be the conjugate acid every time. Okay, so let's do another practice problem, and this is where we're picking up in the notes, I think. Yep. Okay, so yesterday I think we did a problem involving Cn minus. This is where we left off in the notes. So we're kind of going to hit that again, just with a little bit of vocabulary now from what I just said. If Cn minus reacts with water, how is this going to behave? Is this thing going to be an acid or a base? Base. And how do we know? It's negative. And it would be impossible to act like an acid because the definition of an acid is it gives away an H. This guy doesn't even have an H to give away. Right? It can't be an acid. It's got to be a base. If this is a base, this is an acid. Okay, should I draw one arrow or two arrows here? Two. How do I know to draw two arrows? Well, was this strong? Is it one of our strong bases? Nope, it's weak. Well, how about this? Is this one of those strong acids that we memorized? No, definitely not. It's weak. So if the substances over here are weak, they set up an equilibrium. You should not draw a single arrow unless you have a strong acid or base over here. Okay, so now if this is a base, what's going to happen to it? What's the definition of a base? It will accept a hydrogen. Where's it going to get the hydrogen from? From the acid. So that means water is going to take its hydrogen and give it to that chemical. What's it going to turn into? What is it? HCN. Will it still be negative? Well, I'm taking an H positive and I'm adding it on here. If this is negative and you attach a positive, it's going to become neutral. Okay, so we'll just make this HCN and it'll be neutral. And since this was a base, this is the conjugate acid. Does it make sense to you that we would call it an acid? It's got an H on there. Okay, what am I left with? If I take an H off of the water, don't I just have one H and one O? Let's write it like this. Now it was neutral. I took a positive off of it, and that means that it is negative, right? Okay, if this was the acid, then I should call this the conjugate base, which hopefully makes sense because he's negative. We're just going to do like a couple more practice problems to make sure that this all sinks in. All right. Oops. Oh, I forgot to turn the projector on. Doo-doo. Now check out this practice problem. We said that if an acid loses an H, it becomes a conjugate base. When a base gains an H, it becomes a conjugate acid, right? We said that already. So what about this chemical right here? What would be its conjugate acid? Okay, well notice that it's got an H and a negative. This thing is amphiprotic, meaning it can gain or lose an H, right? To become a conjugate acid, doesn't it have to act like a base? Which means it's going to gain an H. If it gains an H positive, what will its formula be? Perfect. And the H2CO3 has to be neutral because it was negative and we put a positive on there. Okay, what if I wanted to turn it into a conjugate base? Well, to make a conjugate base, it must act like an acid. What do acids do? They lose H positives, so take off an H and take off a positive. I'm left with CO3 with a -2 charge. Okay, so we're looking at 2 more examples, and then I'm actually going to let you try a few problems on your own. Check this out. This chemical, HCO3 negative, is turning into CO3 2 negative. Didn't it lose an H? So it was an acid. What it turns into, we call a conjugate base. Okay, but now let's refer to this pair of chemicals as a conjugate acid-base pair, right there. So when you see the AP exam say, identify a conjugate acid-base pair, what are they asking for? They're asking you to identify an acid and its conjugate base. Alternatively, what could you identify? You could identify a base and its conjugate acid. That's also considered a conjugate acid-base pair. So I got 2 different pairs to choose from when they ask you this question, right? Both of those pairs would be correct. What you can't do is list the first 2 chemicals as a pair or the last 2 chemicals as a pair, okay? We're going to skip that. Let's look at this problem. Label the acid, the base, the conjugate acid, and the conjugate base. Okay, so just look at this problem here and see that you're starting with HSO4 negative, and it's converting into H2SO4. So what is this chemical doing? Gaining an H, which means it is acting like an base. Sweet. Does that make sense? If that is acting like a base, then what is water? An acid. Okay, now if this was a base, this will be the conjugate acid, and that means this has to be the conjugate base. Can you identify a conjugate acid-base pair? Give me one possible answer. Samantha, give me one. Perfect. Those 2 would be a conjugate acid-base pair right here. Alternatively, you could have said water and hydronium, right? The end. That's it for lesson 1. Okay, if you can tell me what movie this is from, I'm giving you extra credit. How ridiculous. Oh my gosh, now I've just lost it. Oh my gosh, you guys, now you have to come up with that. It just left my brain. That's it! Yes! Goonies! Jack's getting the extra credit. Sorry, not enough. Anyway, this guy did what we call the truffle shuffle, which is where my brain went when I thought of the phrase room shuffle. So we're going to do a little weird activity that has nothing to do with this picture, but there's my brain for you. Okay, so what are we going to do? There are areas where there are cards around the room. I want you to go to one of those areas and answer the questions just mentally that you see on both the pink and the yellow cards. The answers are on the back, so you're just answering it mentally, flip it over and check, see if you're right. Okay, I want you to go just mentally find a spot in the room and do those problems. For you guys at home, I'm going to take you to some problems here for me. Chelsea, there's some on the other side of Defang back there if you want. Back by Einstein. Okay, so these are the problems that they're working on. What is the conjugate base for H3O positive? If we want the conjugate base, then that means this must be acting like an acid. Acids give away H. So you can think about the answer. The answer is H2O. How about the conjugate base for HCN? Same logic applies. Think about the answer. CN negative. What about the conjugate base for HSO4 with the negative sign? Same logic applies. SO4 negative 2. Okay, so we're going to switch gears. What is the conjugate acid for this chemical? So if I want the conjugate acid, it means this must be acting like a base. And bases gain H positive. So this chemical needs to gain an H, and we're adding a positive charge. When you guys are done, you can totally have a seat. So the answer is NH3 neutral. It goes from being negative to being neutral. What's the conjugate acid for water? Same logic applies. H3O positive. Last question here. What's the conjugate acid of NH3? Same logic applies. We need this to be a base, which means it's going to gain an H positive. That's going to make it an H4 positive. Okay, how do you feel about identifying conjugates? We're okay? So on the test, definitely, I can promise you, I'm going to give you a question where I'm like, here's the equation. Identify a conjugate acid-base pair. Please don't think that you have to choose the conjugate acid and the base, right? You could choose the conjugate base and the acid, and that's still going to be a perfect answer. So it doesn't, when I say conjugate acid-base pair, it just makes everybody think it specifically has to be the conjugate acid. Okay, never mind. We're going to keep going. Lesson 2. Ew. Okay. So let me help you understand how yesterday we said that water can act like both an acid and a base. I don't know if you remember us talking about that. Water is capable of doing that. As a matter of fact, if I had me a cup of water, there'd be 1 million molecules in there. And at that very moment in time where I'm just looking at the water, some of those waters are acting like acids and some are acting like bases. So this is what's happening. 2 water molecules are coming together. Okay, and let me write it like this. So let's pretend that this one acts like an acid. He's going to lose his H positive, and this guy is going to gain it, so it will be the base, right? So what will I end up with on the other side? I will end up with OH negative and H3O positive. Water does this on its own, spontaneously. Isn't that weird? So water can act like an acid or a base with itself. We actually call that auto-ionization, self-ionization. That's what that is. Okay, so now some guy developed a way to measure the amount of H3O positive and the amount of OH negative that's in water at a certain temperature. They found a way to measure it. Okay, do you realize that this would be an equilibrium? And so my K expression would be products, raised to the first power because they both have a coefficient of 1, over reactants, but the reactants are not allowed to include liquid water. If this is liquid water and this is liquid water, then it wouldn't be in the denominator, right? There would just be a 1 here. So basically, this is the equilibrium constant. Well, if I'm able to measure the amounts of these things in the water, then I can take those 2 measurements and multiply them together and get the equilibrium constant. I can actually get a number for the auto-ionization of water. And it is 1 times 10 to the negative 14th at, I think it's 25 degrees Celsius. I'm not sure about that temperature though. I think it is. There you are. Yep, it is. Woohoo! So officially, that is like a major discovery, and we turn it into an equation. We say that K is equal to the hydronium concentration times the hydroxide concentration. And K is a constant of 1 times 10 to the negative 14th at 25 degrees. So if we have this information, we can use that as an equation to solve for how much hydronium or hydroxide is present in water. It's a big deal. Okay, so officially, there's the equation that you need to use. You do not need to memorize the constant. It will be given to you on the reference sheet. This equation is given to you. The important thing you need to remember is that this equation only works at 25 degrees. Because this number is a constant only at 25 degrees, right? So the question that they give you will always state a temperature. If the temperature is 25 degrees, then hopefully that's like a reminder to you, oh, I might be able to use this equation that we just learned. So what we're going to practice for the rest of the period today is just using this equation. How do we use it? When do we use it? That's the idea. Okay, it's on that reference sheet, as I mentioned. All right, so let's take a look at a problem where you might use this equation. Do you first of all notice 25 degrees? Boom, there's my reminder about this equation. Now, they also give me another number. This is the concentration of hydronium. All I'm going to do is plug that number in for hydronium. Okay, so I'm going to plug it in on the right side of the equation. And that means I'll only have one variable remaining, and that's what I'm going to solve for. So watch this. I recognize that this is the equation I want to use because it's 25 degrees. I'm just going to plug in the number that they gave me for hydronium and solve for the other variable. That's it. Very basic algebra. Hydroxide is equal to 1 times 10 to the negative 11. What do you think? Chemistry is so easy right now. Yes. I need for you to be able to do this math mentally, though. So easy. Check it out. It looks scary, but it's really not that bad. If I take the equation with that hydronium number filled in, and I just rearrange it, I can get this. Right? Okay, so how do you do this math mentally? Well, 1 divided by 1 is 1. Times 10, you don't do anything with that part. And then what do I do with these exponents? Do you remember? You subtract them? What's that? I'm sorry. Yeah, so however you want to think about it, but those are really coming from subtracting these guys, right? That's how I think about it. So hopefully that doesn't feel hard to you at all. What if it was 2 times 10 to the negative 14? So then in that case, you would do 2 divided by 1, which is 2, times 10, and then you're still just going to subtract those exponents. Real easy. We just need to be able to do it mentally on the AP exam because they'll give you these kinds of questions in multiple choice and you can't use a calculator. I won't do that to you on the test, but if you want to be successful in the AP exam, we've got to be able to do it mentally. Okay, can you always use this equation? No, only at 25 degrees. Is it possible that they'll give you like 30 degrees? Yeah, but you know what will be different? This number will not be 1 times 10 to the negative 14th. They would have to give you the equilibrium constant at that other temperature. Okay. So I want you to think with me a little bit about what these hydronium and hydroxide concentrations are, because we just solved for hydroxide, but I'm not sure you really know what that is, right? So let's try to help you understand. Let's say I have HCl in this beaker. It's going to break apart, isn't it? How do I know that? It's strong. Okay, what if I put like 100 of these HCl molecules in there? Will they all break apart? Yes, because it's strong. Okay, well, if it all breaks apart, then there's 0.3 moles of H positive in this beaker. You follow that? If there's 0.3 moles of H positive, when that connects to water, isn't that going to make 0.3 moles of hydronium? What I'm trying to tell you is the concentration of the acid is equal to the concentration of hydronium if it's a strong acid, because it's going to completely break apart. So all those H's in that acid are going to directly convert into hydronium. What about if it's a base? Well, if it's a strong base, it's still going to break apart. If it breaks apart, isn't it just going to make a hydroxide for every one of these that's in there? For every one NaOH that goes into my beaker, I'm going to make one hydroxide. So if I put 0.6 moles of NaOH in my beaker, how many moles of hydroxide do I have? 0.6 moles, right? In other words, the hydroxide concentration is coming from this thing breaking apart, and it is equal to the concentration of the base itself. Just like the concentration of hydronium is equal to the acid. If you know this hydronium concentration, can't you solve for hydroxide? If you know the hydroxide concentration, you could solve for hydronium. Okay, I want to do one more. This guy's different from this one. Do you see how it's got 2 OHs? So when that guy goes in the water and he breaks apart, he makes 2 OHs. For every one of these that I put in. Well, I'm going to put 0.6 moles in. How many hydroxides will I have then? Will I have 0.6 moles? Won't I have double that many moles? So does it make sense to you that it would be 1.2 moles of hydroxide then? Okay, so again, what can I do with that information? Well, we have this equation. If I know the hydroxide concentration, I can just plug that in. I can solve for the hydronium. So what the problem is going to give you is a concentration of an acid. And if they give you the concentration of the acid, that's going to be equal to hydronium. So you can literally just plug that in for hydronium. If they give you the concentration of the base, well, that'll be equal to the hydroxide. So you can just plug that in for hydroxide. Be careful, though, if that formula looks like something like that. Actually, that's a terrible example. Let me not do that. How about this one? Then the concentration of the base is not quite equal to the hydroxide. The hydroxide would be double the concentration of the base because of that 2 there. So we would just want to look at a practice problem that kind of uses that logic. Check this out. I have some acid, guys. It's got a concentration. What's the hydronium and hydroxide concentration in it? At 25 degrees. So as soon as I see this, I'm thinking, oh, here's the equation that I want to use, right? The next thing I notice is it's a strong acid. So its concentration will be equal to the hydronium. So can I just take its concentration and plug it in right here? That's all we're doing. So when we plug that in, we just solve for the missing variable. That will be hydroxide. Okay, if it wants the hydronium concentration, this is the hydronium concentration right here. How do you feel? Slightly tricked. Okay. Let's try again. Oh, maybe if I draw pictures, it will help. So I'm going to pretend that I go into this back chemical storeroom, and I'm going to pull out a random chemical. Let's pull out... Here's my... Oh, yeah, that's good stuff right there. Woo, yeah. Let's pull out SrOH2. Is that an acid or a base that I pulled out? It's a base. Is it strong or weak? Aren't you getting annoyed with that already? That's why we're going to memorize those suckers. It's strong. Why is that important? Well, it tells me that really what's inside this bottle is strontium ions and hydroxide ions. There is none of this, actually, because it's strong, it breaks apart, right? So inside this bottle, really, this is what's there. I want to know what is the concentration of H3O positive. Well, I know that there is H3O positive in here because there's water in here. That's what it means when this thing has a concentration, is it's mixed in water. And water contains these two things. Isn't this the equilibrium expression for water? Right? So that is, this H3O positive is in here. It's just not coming from the base, it's coming from the water. But I want to know what its concentration will be. So let's pretend that this bottle is labeled as 0.8 molar. Well, what's my hydroxide concentration then? 1.6 molar. Yes. 1.6 molar. That's my hydroxide concentration. If I have the hydroxide, then can't I solve for hydronium? So all we're going to do is 1 times 10 to the negative 14 divided by 1.6 times 10 to the z, times 10 to the, 0. And that's going to be equal to hydroxide. So it's just 1 divided by 1.6 times 10 to the negative 14. Will that answer be a very big number or a small number? Not a trick question. Times 10 to the negative 14 is a small number, right? So my hydroxide concentration is big. My hydronium concentration would be very small. That should make sense because this is a base. It would not have much hydronium in it. Hydronium is generated from acids. Okay, so hopefully, maybe in pictures it makes a little more sense. Where are we at? Okay, so I'll tell you right now, this is the equation everybody forgets about on the test because we don't use it a lot. So when you're working on lesson 2 homework, there will be quite a few problems that require you to use this, but then we won't use it again in lesson 3 or lesson 4 and lesson 5. So you want to make sure that you keep this in the back of your mind and just don't forget about it. I'm trying to prevent that from happening every year. So we're going to hopefully come back to it right before the test just to be on the safe side. Okay. Why in the heck do we care about a hydronium or a hydroxide concentration? Because you can calculate the pH from hydronium. If you have hydronium, you just take the negative log of it in your calculator. That's what pH is. If you have hydroxide, you take the negative log of that, you get something called POH, and you can actually subtract that from 14 to figure out the pH. So there's like a couple of ways that you can calculate pH from this information that we have. And I know that you guys have probably heard of the pH scale, but maybe you've never seen it for real. So here's one. It starts at 0 down here, and the pH scale goes up to 14. That's because most chemicals have a pH of 0 to 14. But actually, some chemicals can have negative pH, and some chemicals can have a pH above 14. It's weird. But this is a general scale. If you are a chemical that has a high pH, your base. A chemical with a low pH is an acid. And if you have a pH of 7, then you are neutral. So I need you to be able to calculate the pH and then tell me, based on that pH, is it an acid, is it neutral, or is it a base? So officially, 7 will be neutral. If you're 7.1, you're a base. Okay, if you're 6.9, you're an acid. We need to just be able to take the math and classify the chemical as an acid or a base. Those 3 equations that I just showed you on the reference sheet, you don't need to memorize them. You'll probably accidentally memorize them anyway. Let's look at a practice problem here. I'll put that sign up there too. There. What is the pH of this chemical at 25 degrees? What? It has 25 degrees here. You mean to tell me I might be using that crazy equation that we were just doing in the last problem and a pH equation? Yeah, it can happen. It can be required. So it's not always necessary though. Let's take a look here. Can you just identify this as an acid or a base? That's a base. So what do you know about its pH automatically? Should be greater than 7. Okay, so when we do our math, we're going to remember that, and we're going to check to make sure that it makes sense. They've given you a number here to use. That's the concentration of the base. Okay, so here comes back to my picture. All right. So NaOH is the base, and it has a concentration of 0.0012 molar. When I put it in water, it breaks apart. What will the concentration of the hydroxide be? It'll be the exact same as the base, right? For every one of these, I get one OH. So the concentration of the OH should be the same as the concentration of the base. It's in a 1-to-1 ratio. Okay, so I know the hydroxide concentration. Can I take a hydroxide concentration and directly calculate pH? No, because pH is calculated from the hydronium concentration. So what can I do with this hydroxide concentration? That's the only number they've given me, is hydroxide. What can I do? Well, I can plug it in here, and that would allow me to calculate the POH And then I can plug that in here to get pH. That's one way to do it. The other way to do it is to go back to this equation, because it says it was 25 degrees. You could plug the hydroxide in here, and that would allow you to find hydronium. Once you find hydronium, guess what? You can do this equation to get the pH. So you have two choices of how to solve the problem. Okay, so let's take a look at the answer key here. We first have to recognize that NaOH is strong, so its concentration, the number you're given, is hydroxide. You have to make that realization. Now, let's go ahead and use this equation since it's at 25 degrees. Let's plug in the hydroxide concentration. That will give me hydronium. This is hydronium right here. Once I have that, where am I going? Into the pH equation. So I'm going to take the number that I just got here, and I'm going to plug that into the pH equation. Take the negative log of this number, and I get my answer. Look at what it is, 11. Does that make sense for a base? Okay, so that I sort of know I've done my math well. Is this the only way to solve the problem? No. We could have done it the other way. Oops. Is this making sense? Okay. So I've got to teach you one other mental math thing, and this is a big deal for the AP exam. Do you see this little part of the problem right here, negative log of 8.3 times 10 to the negative 12? Can you do that mentally? No, but we can estimate it mentally. And if you estimate it, you would guess the pH to be about 12. And the answer is actually 11, so that's a pretty good estimate. How am I estimating it? What am I looking at? If I'm estimating this to be about 12, what am I looking at? This number here, right? Okay, so if I'm looking at this exponent, that's basically going to tell me the answer to the negative log of that number. So let's do, we're not going to do this pattern here. I think we're just going to do something slightly different. Let's look at a couple problems. We're making good time today, guys. This is good. What's the negative log of 1 times 10 to the negative 7th? 7. Good. What is the negative log of 1 times 10 to the negative 3rd? Perfect. Now, guess what? If I plug in these numbers, I will get the actual answer to be 7 and 3. That's the perfect correct answer. What is the negative log of 2 times 10 to the negative 3rd? It's going to be about 3 still. It's going to be about 3. It won't be exactly 3 because it's not 1 times 10 to the negative 3rd, but it will be close to 3. Should it be slightly lower or slightly higher? So in other words, are we talking closer to 2 or closer to 4? 2. If this number goes up, this number went from 1 times 10 to the negative 3rd to 2 times 10 to the negative 3rd. It went up, it increased. If you take the negative log of a large number, it'll give you a small number. If you take the negative log of a small number, it'll give you a larger number. So it kind of works in opposites. If this number increases, then this number decreases. So to be closer to 2, maybe the answer is like 2.9 or 2.8 or something like that. So on the AP exam, or on the test, I can do this on the test. I'm going to say, what's the pH of 0.004 molar HCl? Is it 4? Is it 3? Is it 5? Or is it 8? Okay, well, which one can I eliminate? Definitely not 8. How do you know? HCl is an acid. If HCl is an acid, then it definitely has to have a pH below 7. Okay, now what I want to do? Well, recognize that that number is 4 times 10 to the negative third. Okay? If it's 4 times 10 to the negative third, and that is the hydronium concentration, then if I want to get the pH, I'm going to just need to take the negative log of that number. So now, what should it be closest to? 3. There's my answer. Technically, it won't be exactly 3, right? If you had to guess, if my answers were, well, let's say 3, 2, and 4. We'll leave those. Then what would you guess? 2 is probably the closest answer, right? Because this is a higher number than 1, then my pH is actually going to be slightly less than 3. So I'm going to go with a pH closer to 2. And if you plug it in your calculator, you can get an official answer. You'll see it's close to 2. Okay. Let's try this one. We want the pH of soda at 25 degrees, and it's 4.32. It's an acid. Soda is an acid that you drink. Okay, what are the hydronium and hydroxide concentrations? They gave you a pH. So, where can you plug that in? Couldn't I plug it in here and solve for hydronium? Or could I plug it in here, solve for hydroxide, or POH, I mean, and then put that POH in here, solve for hydroxide? You could do that. You could put it in here, and once you get the hydronium, go to this equation, plug in the hydronium, and get the hydroxide. So again, you can solve the problem several different ways. I'm just going to show you one way that I solved it, but you could do it differently. Okay, so I'm going to go with this equation. And I'm going to take that 4.32 number, plug that in for pH. I'm going to solve for x. I get x to be 4.79 times 10 to the negative 5th. Guys, if you don't know how to solve for x in this math problem, I want you to see me or go to the past room and ask a math teacher so we can show you how to do this math if you need it. This right here, though, this is hydronium, right? I've answered half the question. I still need to answer what is the hydroxide. Okay, so I'm going to go to this equation at 25 degrees and take that hydronium number I just solved for and plug that in here. If I do that, I can solve for hydroxide. There will be the second half of my answer. But I want you to recognize it's not the only way to solve the problem. So all I think you need is a little bit of time to practice these sorts of problems. And so we're not going to go any further in lesson 2 until we've done that. But that's where we're going to stop for today. Do you have any questions for me? I promise you, the next time we're in class doing lesson 3, there is a little mini lab coming your way. So things will get slightly entertaining for a minute. Hang in there. Flashback Friday is due Friday, so don't forget if you haven't started working on that yet. And I'm going to ask for lesson 1 and 2 homework to be done, I think by Monday is what I said. I don't know if I sent it out in the reminder or not. But by Monday is what we're aiming for. Thanks for listening today at home, guys. Appreciate you. Oh my gosh, I feel like I